what the parabola and the cubic function look like, right? Now, if you were to add higher powers, but they're still even, they kind of still resemble the parabolic shape. See what I'm saying? Like it's still kind of like a parabola. So if I change this to a 6 or something, and just remove some terms or whatever, still kind of like a parabola. If I put another even number, let's say 30, whatever. You see where I'm going with this? Like if we know what a parabola is doing, you can kind of see what any even function looks like. Okay, same thing with odd. Odd has this kind of shape, but if I change it to, let's say, 15, let's make up numbers here. Whatever. It'll have this shape. So he's still kind of like a cubic. So the beginning of the homework, we're just going to be having you match the graphs to the right ones. So I'm like, well, we can kind of figure out the zeros, or you can kind of rule stuff out, right? Now, there's a negative on the x squared. It should be opening downward. So it's got to be B or C. Since it's just degree 2, it's most likely going to be C, right? This is the fourth power function. So, and it's negative. It's got to be opening down. So it's got to be A or B, but I'm thinking B because it's a higher power, it's slightly different, not a basic parabola. Does that make sense? You see what they're doing, right? Now, another thing you need to know is the end behavior. So let's see here. For even function, first let me create a little chart for you. Let me switch to my pivot here. Positive constant. K greater than 0. So if you have this situation going on, but you have an even power, right? If the K is positive, and you're basically, I'm saying that the, how should I phrase this? Okay, I'm going to put it up here. Forgot to make space for this. F of x is equal to K times x to the n. If n is even, the power, and k is positive, then it'll have this kind of end behavior. Which means that as x goes to infinity, so do the y values. The f of x function goes to infinity. If x goes to negative infinity, then the function goes to negative infinity. Okay. Now, if k is positive but odd, but it's an odd power, the n is odd, then they'll have this kind of behavior, end behavior. So when x goes to infinity, the function goes to positive infinity. When x goes to negative infinity, f of x goes to same deal. This one was wrong, my bad. Now, for negative constant, if k is less than 0, right? Same thing for the even power. As x goes to infinity. Oh, wait, let me draw the shape first. One moment. Okay. So we have this shape. So if x is going to infinity, then the function goes to negative infinity. If the function goes to negative infinity, so does the function. Yeah, I don't know why I did that. So, right. Okay, when it goes to infinity, this one goes to negative. When it goes to negative infinity, this goes to positive. Okay, so that's the end behavior stuff you need to know. We'll call this the end behavior of a polynomial of the form f of x equal to kx to the n plus, terms. Where kx to the n is the largest degree. I should rephrase that. The leading term is the official word. Leading term. All right, so knowing that, now we can kind of pick out the questions a little easier. You agree that the leading coefficient, I'm sorry, the leading term is 1/5 x to the fifth. Okay, what is the highest degree of this polynomial? Right, the highest power is the degree, and it determines the end behavior. So it's going to be the second case we have here, right? This type. We have an odd power, and the 1/5 is positive, so it has to be this kind of shape, right? So it rules out A and B right away. Most likely it's going to be C because it's a little weird looking. And this is a fifth power function. Eventually they ask you straight up what the end behavior is. So this would be this last case, right? So what is it doing? Right, it's rising on the left, falling on the right. You guys agree? Yeah, so left rises to the left, falls to the right. Okay. And that one's boring. What about this one? Well, it's an even power, but it's negative, right? So then it should be this one. It has a parabolic shape. Because it's negative, it opens down, right? Falls on the left, falls on the right. Any questions on this idea? It's pretty, all we need is the these definitions, right? For this chart. Okay, let's move on to something else. You guys are cool on end behavior and the shapes of these types of graphs, different powers. All right, so eventually they try to have you find out every little detail and try to let's see. I think it's a good one. Yeah, let's do 18. I think that'll be more interesting. We'll do it on the paper because there's a lot of little details. So the first thing you should do is find the zeros. Do you guys remember how to find the zeros? Now, what do we have to do? Yeah, set the whole thing to zero, and then we do what you said, Carlos. We should probably factor though, right? Might as well. Does this factor pretty? Doesn't look like it. Interesting. That's lame. Yeah, I'm gonna make my own question because I want you to see an easier one before we do a harder one. Me, just ignore this. Let's just make it up. Here we go. Sorry about that. I think this will be nicer. So given this guy, part A was find the zeros. So we should first factor everything. I made one up that's factors a little prettier. Okay. So we said we need to set the function to zero. In order to find it, and once you have it set to zero, you set each piece to zero in order to find them. So x is 0, x is -2, right? What was the next part? Determine the multiplicity of each zero. Oh, determine whether. Let's just rephrase it. Okay. So multiplicity. All that means is like how many times did it appear? So basically, this is two of the same type of zero. This is a single zero. So x equal to 0 has multiplicity 1, which is odd. X equal to -2 has multiplicity 2, which is even. So 2 because it has a square on it. If there was 4 of them, then you'd put a still be even, but it'd be multiplicity 4, right? Because anyway, just a side note. I don't know if that helps or if that's making it messier, but you hear what I'm saying, right? Does that make sense? The term right here, this x equal to 0, this factor has a 1 on it. That has multiplicity 1. So 0 is a number that caused it to be 0, and it has multiplicity 1. -2 caused it to be, that's the location of the 0, but it has multiplicity 2 because of the factor has a power on it. Like if you had another one that had like a 3 or something, then you would say 3 odd. So here you would just label them like, all right, which one goes where, etc. Okay. So at this point, you can just graph it and figure out the turning points. But there is a formula for turning points. Let me look it up for you. End behavior, that's the formula we're going to use. Yeah, n minus 1. So basically, the whatever degree you got, subtract 1. Okay, so part C was determine the number. Okay. I'm just going to shorten it up. Determine the number of turning points for the function f of x. Now, can you tell what the degree is when it's factored like this? Or like this? Well, let me show you how to count them. That way you don't have to multiply it. Now, here we have 2 of them, 2 zeros. Here we have 1, so 1, 2, 3. The number of factors can kind of help you count to the degree. We got a quadratic times a linear, so we should add one more if we were to multiply it out. But you can kind of just count them. If I had like 3 of these and 2 of those, then it would be 5. And if you didn't know that, you would have to multiply everything and then figure out what is the biggest power. So it's easier to just add them up yourself. Okay. So the degree n is 3. Therefore, the number of turning points is 2. That makes sense? Can you guys figure out the degree without multiplying? Okay. Essentially, that's all you would do here for all of them. The factoring and the finding the zeros might be harder or easier, just depends. Like here, you might have to do AC method. Here, do the GCF first and then just factor the next part. Here you might have to do quadratic formula, which I don't want to do. It's just tedious. But you see it's the same thing, right? Trying to find something different. Do you have any questions about the concept? Does it make sense? Can you find the zeros? Can you figure out the multiplicity? And can you determine the turning points? This one has a couple of zeros. Let's do 23, I guess, just in case. Okay. Saying, well, here they're just asking us to graph. Well, that's stupid. It's fine. Let's pretend that they asked for more. Factor this guy. So find zeros. Or B, determine the multiplicities. Hopefully it's an interesting example. I just picked it at random, but we'll see. Factor by grouping. Let's see if that works, right? You gotta set this to 0. So now we got 3x squared in common here, leaving us with x plus 1. Here we got minus 9 in common, leaving us with x plus 1 equal to 0. So now we got 3x squared, put some brackets so I don't confuse myself. Factor x plus 1 from, whoops. Dang it. Okay. This part factors with the difference of squares. So that'll become some grossness. Yeah, you know what? At this point, what we should do, so it doesn't get weird, let's set each one to 0. And then just solve it separate, because we can at this point. So x would be plus or minus root 3, right? I'm not liking their examples today. Sorry, guys. I'm trying to pick a simple example so you can understand what I'm trying to show you. But this one is gonna get weird. But oh well. So the factored form would technically be this. But you see how that's kind of strange. But it's fine. Those are the zeros, plus or minus root 3. But you see how each one is technically multiplicity 1. You find a picture before we move on because it's still bugging me a little bit. Here we go. This is a better example. Just to get the point across. Can you see the purple math thing I opened?
Yes.
Okay. I mean, I'm sure you get it. I just want to make sure that everyone gets it. So if your polynomial is in the factored form like this, you already factored it, everything's said and done, right? Each of these zeros has a different multiplicity. So once you set it to 0 and solve it, you'll have zeros for -5, -2, right? -5 makes the first one 0, -2 makes the second 0, 1 makes the third, 5 makes the next, right? If you solve for it, you'll get these values. See how they're solving it here? So now all you got to do is check the number on the power. So that factor has multiplicity 3 on the first one. The next one has multiplicity 4, and so forth. What's interesting though, let's go ahead and see if we can graph it. Maybe it'll be pretty. No, I'll just graph it myself and hope. Okay, this is a ugly picture because I need to adjust the axis here. That's too big. Here we go. A little better. Let's see, maybe slightly smaller might be better. Okay. So we had x equal to -5 is corresponding to the first factor here, x plus 5 cubed. Since it is an odd multiplicity, it will cross the x-axis and go over. X plus 2, which responds to the -2, 0, bounces off that location because it is an even multiplicity. Same thing here. The -1 right there will bounce off of it. The last one is odd at 5, it'll cross. Okay. So this guy, so the multiplicities mean something. It determines the behavior of the graph. Okay. Are there any questions on that idea? Okay. So now I've kind of already used this fact, but um, if something is a zero, then it's also a factor. Let me find the official. It's in the book and homework, but I'll just put in my own words. It's fine. Can you guys see the paper? So, um, if K1, K2, K3 are zeros of a polynomial, then x minus K1, x minus K2, x minus K3 are factors of the polynomial. So real quick, find the polynomial of the with the given function. So here they're saying number 24. The given zeros are x equal to 0, -6, -5. So f of x is equal to, right, x minus the 0 times x minus -5 or -6 times x minus -5. So since those are all the zeros of the function, then I can write it as factors, which would give me x times x plus 6, x plus 5. So that is your one possibility, right, that goes through here. Okay. So that's all you got to do. Just put in that form and you should be good. Same thing for 26, 25, 26. The only difference here, you would have to do x minus this entire thing and x minus this entire thing, then simplify. All right. I think that's pretty much it for this section. You guys have any questions on these concepts? End behavior, even and odd functions at higher powers, multiplicity. Sorry, got lost in thought there. Synthetic division is the next topic. Let's take a 10-minute break there, and I'll open up some of the homework. I think I may already have. I don't remember. Well, I'll check. Okay, we'll start this in just a moment. So first we'll divide with the actual numbers, and then we'll do the real one. Let's do number 8. Yeah. Oh, it looks like it sucks, but okay. Use long division to verify that y1 equals y2. So basically figure out that these two things are the same by dividing them. Let me switch over in just a moment. Okay. I'm gonna do a little side example over here. Let's do 5 divided into 59 or 595. Just making it up. All right. The algorithm, right? The pattern was simply you first see if you can divide the first digit. If you can, we'll do it. It goes in one time. 1 times 5 is 5. And then you subtract it, right? You get a 0. Then you bring down the 9. 5 goes into 9 one time. 11, 1 times 5 is 5, and then you subtract it again. The remainder goes down here. Bring down the 5. 5 goes into 45 9 times. 9 times 5 is 45. If there was a remainder, you would have the remainder over the quotient being added or subtracted to the original piece. We don't have a remainder here though. But this pattern that we just did is the same thing I'm going to do, but with this guy. Okay. So x plus 2 dividing into this. Because we all know that a fraction is the same as division, right? This dividing into this. So it's very similar to what we just did, except they're not digits, they're terms. And you're using the first term only to divide into. So the question becomes, how many x's do go into x cubed? Yeah, it's kind of right. But let's do the scratch work. What does this
I
reduce
have a
to?
quick I have
Oh,
a
what's
quick
up?
question, sorry.
Mm-hmm.
I think I just read it wrong, but can you go back to the homework tab real quick just for a second? Because I wrote 2x squared. Okay, so for y1, it's x3 minus 2x squared.
Oh, I forgot the 2.
Yeah,
Oh, thank you
sorry.
for.
I thought that I wrote it wrong. I was like, wait a second.
No, that's very good because this is a long question and I need to know right now. Thank you. Double check everything now. Okay. Okay. Let's start over. So we said x goes into x cubed, right? But when we say that, this is technically what we're doing. We're dividing into it. So you agree that they would go in x squared times, right? You see what I'm saying? When 5 goes into 5, they cancel out and leave a 1. When x goes into x cubed, one of these cancels out, leaving you an x squared. That's technically what's going on. Right, so now the next step, you do 1 times 5. So x squared times this x plus 2. So x squared times x plus 2. So this piece is what goes down here. But you need to subtract it, just like we subtracted the 5. Are you guys still with me on the pattern? Because it's kind of weird. Nobody likes this for some reason. Okay. So if I put a minus on the entire thing, do you agree that both signs would swap, right? You see what I mean? So technically you would be subtracting this quantity. So x cubed minus x cubed is a 0. Negative 2x squared minus 2x squared would be minus 4x squared. You guys with me up to this point? That's the first iteration of this pattern, right? We're basically at this point. We subtracted these two, got a 0 and brought the 9 down. Now I'm going to bring the 5x down. The next step is how many x's goes into negative 4x squared? How many 5's went into the 9, right? Negative 4x squared over x is minus 4x. Now we do minus 4x times x plus 2. That'll give us negative 4x squared minus 8x. So negative 4x squared minus 8x, but subtract it. So we need to subtract this nonsense. Negative 4 minus minus would be plus, so 0. 5 minus minus 8 would be plus 13. Yes. Is this okay so far? You just keep going until you can't, until you have a remainder and this x is too big. Yeah, you need to practice it quite a few times. It's this pattern over and over again. So now, if you divide 13x by x, what would you get? My gross scratch work. Oops. Yeah, 13, you guys are right. So 13 times these two terms would be 13x plus 26. Bring down that weirdo 1 there and subtract this. So we would get 0 minus minus would be minus 27. So that means when you divide this, you will get this quotient, right? The remainder algorithm says you'll get the quotient plus the remainder over the divisor because I can't go any further. So remainder is a negative 27. But you always write it as over the divisor, right? So is this in fact the other form? Yes. Okay.
can you move the paper a little bit lower? Sorry, so I can see like the bottom.
This way or the other way?
Other way.
So use to use long division to change it into this form. It's not very pretty. Do you have any questions along the way? Any of the steps? Okay. So I know it's a yes or no question, but I'm pretty sure there's going to be a test question that wants you to do all those steps. Right? It's not a multiple choice question. It's always going to be about process. Here, they're just straight up telling you do the long division. They're not having you check. So when you do the long division, you'll get something like y2 that goes here for number 9. Okay. So this is y1 and you're trying to get y2, essentially. All right. Let's do synthetic. This one's a lot nicer and I like it better. Synthetic division is very good whenever you're dividing by factors that look like this, where it's just an x. It's not like a 5/3 x plus 2 or something strange. If it's just a single x minus 8 or whatever, it'll look like this. I mean, you want to use synthetic for this type. Okay, so I'm gonna move on. You guys cool on 8 then? If we're short on time, I do a couple more examples here, but feel free to bring questions about this long division because I know it sucks. I'm not gonna lie to you. No, 8 is what you're doing. This is on the bottom of the denominator. X cannot be 8. Oh, for question 8. No, not really. They're asking us to do long division. That's the point. Now, if you're asking, is there another method or different route? Maybe, yeah, but that's not what we're doing. Like I could easily use synthetic to get me to there for this particular question. I might even be able to factor and cancel a term, maybe. But I do have to learn long division and just do it. Using the divide this guy here. Okay, so let me show you the synthetic. I think you'll like this one. So maybe you've done it before. I don't know. So I like just do a little bar here. So whatever I'm dividing by, x minus 8. So if I'm dividing by this, then I use the 0 to divide by. All right, 8 would make the 0. Now, check if you have every single descending power. You have 3, 2, 1, 0. So we're good. We don't have to add any placeholders. If there was one missing, you would have to add a 0 for that term. So now just write the coefficients. And then you can begin. Now, again, if there was one missing, you'd have to have a 0 for a placeholder. Okay, so this is how it begins. This is the pattern. Bring down the 3. That always happens. Then you begin. 8 times 3 is 24. Negative 32 plus 24 is negative, is that 8? Now again, 8 times negative 8 is negative 64. Add them up. Negative, positive, sorry. Positive 3. 8 times 3 is 24. This is a 0. If you get a 0 at the end, that means that what you were using to divide is a 0 of the polynomial. So x minus 8 is a factor of this polynomial, and it divides evenly. So what would the question say again? Just divide. Cool. So that'll be, so whenever you do a division, you're basically canceling out a factor. So it'll be reduced by a power of 1. So currently it's a degree 3. So it'll go down to degree 2. So use these as your coefficients for the new polynomial. So this will be 3x squared minus 8x plus 3. So 3, negative 8, 3. And that's it. So this is the divided polynomial. That would just, so it's basically what we found. It's like finding this piece. If you have a number at the end, then that would be the remainder piece. We had a 0, so we're good. Is there any questions on this? On synthetic?
I like it a lot better.
Yeah, it's a lot better. I try my best to use this whenever I can, but if I have to do long division, then I'm gonna do it, but I'm not gonna like it. There's only a few times where you have to. Yeah, yeah, always bring the first coefficient down. But I might have one question where you have to do long division and the rest just do whatever. But there's a couple of instances where you have no choice. Let me see. Okay, I can find an obvious question. Yeah, I'll get you, Daniel. No worries. We're just about done anyway. Let's do one more synthetic and we'll call it a night. Okay, so that was 10. So you guys cool on number 10? All right, let me write this question down. You could still do long division and get the same answer, by the way. Just saying. Okay. So if we're dividing by x plus 5, use -5 as your divisor piece. Make sure we got all of the powers in order. 3, 2, 1, 0. Yeah, we're good. So 6, 38, 35, -25. Bring down the 6. -30. Add them up. All right, let's go through this. Let me slow down here. Bring the 6 down. So -5 times 6 is -30. Add them up. 38 minus 30 is 8. -5 times 8. Add them up again. -5 times -5 is a positive. We got a 0. Cool. So that means that this guy will turn into, right? Let me just write it one more time. Into these coefficients here. So it was a cubic divided by a linear term. So it should be reduced by 1. We should have a quadratic now. And that's it. All right. You guys have any questions on the synthetic? I'm gonna take roll. Seem okay? All right. Try out the long division a bunch of times and let me know. Bring some questions next time if you like. See if you get stuck. It's gonna take some practice. The synthetic, I feel like once you do it twice, you'll get it. The long division will take some time. Okay, Abdallah, you here? Noman?
Here.
Trevor? Okay. Joshua Correa?
Here, sir.
Megan Dean? Okay, Madison Ella Dunlop. Stephen Fogel. Alexander Garza. Jorge Guevara.
Here.
Kyler Just. Liliana Manila.
Here.
Victoria, I think I saw you here.
Here.
Jose Mauricio.
Here, sir.
Victor Ramirez.
Here.
Jaden Ramos.
Here.
Jolene Cias. Miranda. Oh, you're here, Jolene. Sorry. Zara. Carlos Velasquez.
Here.
Frederic White. And Dylan Willis. All right, guys, we'll stop here. Let me know if you need me to extend anything. I feel like I already did, but if it's not open, let me know. Can do that real quick.